Okay, so yeah, I'm Marco Esposito working for Cosine. I'm gonna talk about a program, GSTP program called HyperCube. It's all about designing, building a full system for doing hyperspectral imaging from very small platforms, so a miniaturized hyperspectral system, and what we like to say for real-time inspection of the Earth. Real-time inspection is because we want to emphasize that is an operational more than a scientific instrument. So we wanted to create something that was able to give a snapshot of situation on Earth, so an early warning, and deliver this kind of information, not doing the full science that we leave for bigger systems. The other thing to clarify on this slide is the name. So the ESA program is called HyperCube, but along the way we changed the name of the product because HyperCube was already used by some others, so we want to just be unique, so we changed the name, registered as HyperScout. So sometimes if you look around the web, you can find both, but it's the same thing. So we were asked to face a very big challenge in the beginning, so to come up with a solution, a full turnkey solution for enabling hyperspectral imaging from nanosatellites for early warning applications. And that was mainly for being able to launch constellations that nowadays is becoming more and more popular. So we see many new ideas and initiatives. We just read about Elon Musk asking for 4,000, I think, I read, satellites to be launched. So it's becoming a serious business. When we started, let's say, some years ago with our internal developments and then meeting with Luca with kind of similar view on the long term, we're actually still one of the few. Now it's becoming real, let's say, spread all around the world. And so started as a technology push activity, so really to see what we had in our hands already as a technology at Cosine and also in ESA. So many of the programs that are currently running in the GSTP, TRP some of those are contributing to our system. So it's not only about us, but it's what Europe is actually doing. And in that sense was a technology push. So we started what we have on the table and how we can push it to be really miniaturized, really compact, but still delivering useful information for the application we wanted to. At the same time, being this an exercise devoted more for commercial applications, really to sell can be one, the product itself, but also enabling servicing with it means that it has to be commercially appealing, means the very hard time we had was due to the fact that we wanted to select a system was still reliable, or components and engineering, but low cost, or what is low then is debatable, but something affordable for commercial people, not for institutional customers. And for that we put together, let's say, thinking from many different parties, or from scientists, in order to tell us what is something feasible in terms of final geophysical products to be sold later on. And is, of course, some commercial parties, satellite manufacturer to get more input in terms of spacecraft performance as well, because it's playing, the system in the end is the full thing, so plays a very important role. And also we realized that we had in our hands something that would change completely the way of space assets are using in space. So before we had very big satellites with big ground control centers, with big processing chains on ground, so we actually were reversing the full way of thinking. So everything processed on board, of course, with the limitations that are together with what we want to do, and minimize what is on ground in terms of infrastructures. And also using the system for different applications by using the same product already in space. Then this was the main driver and was also the, let's say, the main target of the overall project, beside, of course, the technical requirements that were, let's say, set as a target, of course. Then what I want to mention specifically, there are, let's say, many issues, many challenges with this concept, but just few to give you an idea, is one, together with SmallSat, you get also the very small bandwidth. So whatever you want to do, you have to make sure that with few megabits per second, you can actually deliver the information you need with the timeliness that you set. And for this, let's say, the idea of reversing the way of doing things. So try to download the information and the position of the information is belonging to. So not anymore the full data set raw data, and especially with hyperspectral, most of you will know for sure that we are talking about 4 orbits, terabytes, so it's really huge. Already on big satellites is a problem. On smaller satellites is really the bottleneck completely. And together with this, we get also at least the time when we started CubeSats or nanosats, they were really unstable, let's say. So the AOCS system would not guarantee a certain pointing stability. That for us, since you will see we are a push broom system, was kind of needed. So we took this into account, not to wait for them to become better, but we made a system that is resilient to such instability from the beginning. Now, of course, things are getting better and better. We see these platforms are performing much better, so for us it's an additional asset. And talking about a small system, this is really small, so about 1 liter. We needed to have the full thing. The consortium was led by Cosine, so as a Cosine we were, let's say, the prime, but the system house, so we're really building the full system. Means optomechanics, but also electronics, and making sure that the low-level software is there in order that we can operate the system safely. And then we had Vito from Belgium that brought in very multi-year experience with hyperspectral, with multispectral system for vegetation and all the way of processing this data. So they were are in charge currently. The program is still, let's say, the following already started. In charge of the level 2A, we call level 2A is for us data cube. So the hyperspectral data cube fully georeferenced and corrected for any features that the system would be inherently delivering as well. And all these heritage is coming from probably, as I said. So for us was really a stone, let's say, to have these guys in. TU Delft in charge of the level 2B, so really the application, the geophysical parameter to be delivered in the end. Was nice, also very clear interface between the two institutions. Then SNT from Norway in charge of coding these algorithms into operational software, high-level software. VDL in Eindhoven for manufacturing the optics that we have designed. And also they did a great job. So ISIS in for supporting us with interfaces to our nanosat platform. And IMEC from Belgium, as a consultant, didn't play, let's say, a real active role during the project, but in the beginning they gave us some consultancy about the filtering technology that we would take into account. So altogether it's a very strong, so the payload is very small, but the consortium is very large and the capabilities are enormously big. Just the study logic, how we started. So we, first of all, the project was phased. We had 2 phases. Phase 1 was ending with a design review, so to making sure, since the challenge was very high, and of course ESA wants to make sure that things are not, let's say, going in the wrong direction. We had a very strong checkpoint at the end of phase 1 and design review, making sure that, let's say, the project, let's say, the system design compared to the requirements were kind of compatible, so we could step into the phase 2 where we would build a system, an engineering model. So we started with, let's say, with 2 clusters of activities. So application analysis, that was very important in the beginning to set the starting point and where we wanted to go, together with level 2A, so the data cube finished requirement specification. So together we came up with a product that could, so a level 2A product could serve different applications. And the applications were selected based on science case, so scientists giving us consultancy and us looking at the market. Then the other cluster of 2 was more system requirements and ground support equipment and onboard data handling. That's another crucial point of the project. Then we had a review about the requirements and the first mission scenario. We stepped into a phase where we were detailing a bit more these discipline, let's say, these topics. And we had a design review where, let's say, we presented different options in terms of optical system and electronics and so on, and we passed that, so we stepped into phase 2, where we detailed further the processing chain, the system. Then we stepped into an assembly readiness review, and we built the system, test readiness review, the typical flow, let's say, and then we verified the instrument itself and the software in 2 separate sessions. And then we had already a final review. So this for us is a short version of the final review we had already in May. So the applications that we developed were selected based, as I said, on the technology available, but also on the, let's say, the added value that this system could provide to these kind of markets or application clusters. So we looked at quite a lot of applications. We did a down selection, so we had to do this 5. So basically, the system, the processing chain now is capable of doing all these applications already on ground process on the system on ground. Now we are going to see in orbit which ones we are going to try. And so vegetation conditions, we are talking about vegetation indices, so NDVI and others. Crop was a requirement, so we are actually calculating the FAO factor, so the KC is called the crop factor. Fire hazard is one of the applications that, based on moisture index, would be able to deliver the fire hazard, so it means non-detecting fire already developed, but telling to users, to customers, whether there is high risk of fire taking place in some of the areas. Flooding, applicable in many areas in Europe, and a more general change detection of land use and land cover. And that is a very powerful one as well, where we were looking at detecting changes, not only changes in, let's say, geometrical wise, so things are changing geometrically, but also spectrally, so of spectral content wise. And that would tell you, let's say, whether there is a need to look more into that area, so whether you really need to go there perhaps with a UAV or with any other, or perhaps with a high resolution satellite, and like Strigo that we heard before, to really check in detail what is happening. We can tell every, for example, hour whether something is happening with this one. The other interesting part is the modus operandi. So given the number of applications that can run on board, and with the level 2A build for each, let's say, region of interest, on that level 2A we can develop different applications, means that we can have 2 ways of working, whether for each of the field of view we calculate all these parameters, or that's more efficient and makes more sense to change based on the region we are flying over the related application. For example, if you are flying in let's say, South Europe, where let's say fire hazard is more interesting, whether if you're flying North Europe where flooding, or whether we are north of US where actually the agricultural part becomes more intense. So it becomes multi-purpose and a very efficient way. Or if you have a constellation, there are then, I mean, you can start thinking of many configuration constellations with different platforms, with different applications, each can talk to each other, and so on. And this is all the result of brainstorming sessions with all the guys I told you before. So let's say the first result was this kind of parameters we found out to be interesting to the communities, with the ground sampling distance area of interest on Earth to get an understanding on how many systems we will need, or with the field of view as well. Number of spectral bands, so whether a multispectral, as we said before, sometimes multispectral is good enough, so we just go for a few bands. But having an hyperspectral in orbit doesn't mean that you need to use the hyperspectral information every time, but you can select just the bands you need and work in a multispectral mode for such an application. Still, you have the hyperspectral capability for more. And the resolution, let's say, from 10 to 20 and more for some of the applications. A signal to noise ratio, that was also interesting because the system, as you understood, is very compact. So the radiometry performance are limited compared to other systems. So for us, this was very important to set the starting point. Then about the architecture. So let's say the challenges were many. So just few mentioned here again. So optical electronics very compact, still reliable for a certain lifetime. The other aspect related to the question of this morning to Strigo, so how many you can build in how much time. So we really start with this requirement as a strong one. And so one of the things we said, well, we want to build optical system without aligning them optically, at least not every time. So most of the effort went into find a procedure, a process such that we could skip in the end, in the operational stage, to go there every time with an optical alignment, interferometry, and so on, but just mechanically making sure that is reliable enough to produce them in series. And as I said, large field of views, this is a reflective system. So this was very hard because we had a very wide field of view across track. That is already a strong requirement for a reflective system, let's say. Then finding out what are the performance of CubeSat back then. So with this instability issue, we went for a wide field of view also along track, so that even though the system is unstable, at least we can make sure with our field of view that we don't get gaps during the acquisition. So we get, we'll see, 30 by 16, very large, very difficult to correct and to design. So compromises, trade-offs, and we made it. Delivery of end-user information, this goes together with real-time. So these are two strong ones. So end-user is the first thing. So we are used to calculate things on ground, getting information also from other sources, but we want to do real-time on board. So this together was a strong one. As I say about instability, and of course low power. So this system is small, means that solar cells, solar panels are small accordingly. You get limited power. Then you want to do all these challenging things with a few watts. The, let's say, specification of the system as was designed and built, assuming an orbit of 600 or 300 between brackets. The parameters are related to this altitude. So field of view, as I said, 31 by 16, so extremely large in both direction. Ground sample distance at 600 of 80 meters. If you go down to 300, 300 was in the picture because of ISS possibility as a launch base. But also, I mean, nowadays with electric propulsion, you can actually think about this kind of orbit. So stepping down to 300 to get a bit higher resolution, then stepping up again to continue doing monitoring. Azimuth of 350 or half of it, basically. The detector is a 12 megapixel sensor. We used, not completely, we used 4000 by 2000, so 8 megapixel effective, where the hyperspectral information is. Then there is another part that is not used. Then a spectral range, we got, in the end, two configurations. One because of the synergies with the CHIN development at ESA, this direct deposition of the filter on the chip from IMEC, that is currently running. So we already took that into account, so you get what we called HyperScout high resolution, high spectral resolution. So you get about 5 nanometers and a spectral range between 470 and 900. Then, since we are, to be honest, are running pretty quick, so that development would take a bit more time, perhaps not. So we want to make sure we have a configuration that is operational. So with the detector plus a filter coded on the glass and not on the chip, we get actually a bit more spectral range. So we get into the near infrared to 1000, even though from 400 and 1000 you get, of course, a step down of the efficiency of the sensor, so you get less signal, but still you get something, and a bit wider spectral resolution, about 12 nanometers. Then signal to noise between 50 and 100. Let's say in average we are, let's say, more towards the 50, but peaks can go a bit higher than 50. But we made sure this kind of dynamics or performance were good for the needs we had. And then a mass, 1.2 kilograms, about 1.2 liters, and an average power of 10 watts. This is how it will look like if you, with the cross-section of the system. So it's a 4 meters actually. We started with a TMA, but along the way became something, no name I will say, so perhaps we can think on new name. You see the entrance aperture, then getting to the first mirror, secondary mirror, third, and then there is actually a folding mirror to get to the FPA on top, and the electronics plug in the back. By design, the system is distraction limited over the entire field of view. Of course, building it, you get degradation here and there. We are still in the phase of optimizing the full optical performance, still with the constraints of being able to build it, to assembling it without optical alignment in the future. How looks like the CAD in typical CubeSat structure. To be honest, this was at the time of this GSTP project. We already are running the second one for flying it, so it now looks slightly different, but it's still pretty much this one. So where you see the system plus some of the boards all around the telescope. such that also to use these boards as a heat source when needed. So try to couple the processing plus the thermal stabilization. That is completely passive, of course. There is no way to do differently. Operating modes, I'm not going to go too into details, but to emphasize that the effort went into make the thing modular. So in the typical, let's say, processing mode, you have sub-modes, let me say. So you could start by, if you have, perhaps if you are plugged on a bigger platform, because that's a possibility, perhaps you want to download the raw data, so you can still store and download those. Or you can actually, we have modules that deliver an output that can be downloaded as well. So you get level 1B, level 1C, level 2A. And the level 2A, then you can do different things, select few bands, or we had the University of Delft actually delivering a new way of selecting bands. So to select the bands with the most information contents, or by merging bands in order to make out the best information out from what you have. So this is one actually of the product. And then there are typical ones for any satellite missions. Calibration, so no equipment on the board, only vicarious calibration. So we investigated during this project. Now we are in the phase of really looking, actually, because we have to fly soon, what kind of bodies we could use. So the moon, invariant sites, random scenery on ground. So actually you can get out a lot from bridges, buildings already if you want to do geometrical characterizations. And let's say many others. Of course, cross-calibration with other satellites, with Sentinel-2, for example, where there we can be really complementary by cross-calibrating or even delivering more points in between the data that Sentinel-2 delivers. So we could fill, let's say, some of the gaps with less, perhaps, accuracy on the results, but cross-calibrating on them once every week, for example. That could be a good way of working together. Then we build the system, just few pictures you see. So the system were mainly 2 blocks, so you plug it together. As I said, VDL, manufactured meters. You see the electronics with the large FPA, so with this electronics of the EM engineering model. And so I have to say that all in all, the system is really rugged. So by nature is really resilient to vibration and shocks, but also is really a thermal, all same material. And but now, we are doing a proper qualification campaign. So we are going through together with this the full set of typical environmental for a low Earth orbit. We are doing a campaign right now for radiation testing in Bolshoi Institute in Switzerland for especially LECHAP, for qualifying our LECHAP protection system. The system, how it looks like. So this is DM again. You see the FPA on the side, and the picture really shows how small it is, and therefore how flexible in the use as well. So we can plug this system on nanosat, as I said, but also on big platforms, like for example will be with we were looking with Medialario, we're using together with Strigo. So you could use this system as a viewfinder. So on the same platform, looking forward, perhaps 2 of them, so you get 60 degrees field of view. And with real-time processing of change direction, you can tell to the Strigo payload where to look because of the few degrees, 1 degree I heard this morning. Field of view is very narrow. This you get 60 with 2, so you cover basically almost full, I think 2,000 kilometers about, and then you can make best use of high-resolution payloads. Testing, so will be quick. So we did different testing at different locations. Some tests were done on VDL when the optics are manufactured. Some at TISA here. We made use a lot of the facility at TISA thanks to the very nice cooperation. So we did, let's say, interferograms, interferometric measurements, different phases. At Cosine, we did let's say, at system level, optical and radiometric characterization. So we looked at all the geometrical, spectral, and radiometric response of the system. So we are supposed to stop at TRL4, but we did, I think, 1 step more. We did a thermal vacuum characterization as well, and the first test, single event effect test, already during this engineering model building. The software performance, so all the, let's say, high-level products that I mentioned in the beginning were tested in terms of performance and of speed, let's say, for what concerns the software itself. So the application we selected are processable, let's say, between 40 and 80 seconds as they are now. And we are now optimizing them to make some improvement even. And with, of course, the very important thing that what has been done and been taken from ProbabV, so a very tested way of working and shape it and tailored for our application. You can imagine, so what I was saying before, so using the platform based on what you are flying over, so acquire and process in parallel, that will be something we are looking at, so you can really optimize the overall mission scenario. A typical, let's say, mission scenario you can expect with such a system. So this was one of the examples that we are going to try in orbit to fly over different locations along one orbit where different parameters are relevant and try to calculate them to deliver to a ground station somewhere close to them and see whether we could, let's say, supply all these users in one orbit even, so it becomes really attractive. Briefly, let's say we look at different ways of using this one. So you could guarantee a global coverage with a certain revising time. It can be daily with a number of satellites, but you can even go to regional monitoring. Even we did some simulation, even half an hour. For example, we made the case of the Netherlands. We could do flood detection with a revisit time of half an hour with 12 to 15, 16 satellites. So, and as I said, given that we looked a lot at the commercial value, so this could be something affordable with a fraction of what usually in space businesses take into account. And the nice thing is that doing this with ESA, you get a level of quality, of course, with us pushing on the commercial side, that is really a compromise, so really in the middle for serving the commercial market with a good quality stamp from ESA. Yeah, 18 months we built DM. So I would say a very fast-track project because it was from scratch completely, especially for the algorithm and software. We believe we have reached TRL 4 fully, and to be honest, we did a bit more. So everything worked as planned. For the telescope, we are still now working for making more reliable, so the full procedure for assembling it and aligning. But the backbone of the software of the electronics is all working. And so we already, as I said, we stepped already in the follow-on phase to demonstrate it. And so we are building now the flight models, are gonna be delivered at the end of January 17. And so it's gonna fly someone in second quarter 17. And as I said, we are doing this with, in the end, a full qualification approach. So we are not neglecting things. And we are, let's say, looking at, let me call a HyperScout configuration that we pathosize in a way together with the Medialario. That could be a test case in the beginning, how to use this system. For example, we can think about 4 of these HyperScout together, 2 in the visible near infrared, 2 in the shortwave, for example, where we can detect clouds and see whether it makes sense to process or not. And but you can go on the website we made for the product, HyperScout.nl, where you can find a bit more of ideas where to use it, that you can actually contribute if you want. So you can get interaction with us, and we are proposing this flight mission also to users to join, and in order to plan, let's say the first 6 months are kind of booked for the demonstration, but then after that, if the system behaves well, we can exploit it with customers. As I said, so as we region, the beauty of doing meters is that you can, it's achromatic. So we plugged in a SWIR sensor just for testing it, and so actually the system, we knew that, but it's nice to see. And we are now playing also with the thermal infrared system, so that this opens new ways of cooperating with you and with the users. I thank you, and I thank you, ESA, of course, but also the NSO, the Norwegian delegations, and the BELSPO from Belgium for giving us this opportunity.
Thank you, Marco. So we do have time for questions.
Thank you, Marco, for your nice presentation. Out of curiosity, I think for the fire hazard, You were talking that you have a user community that is behind that. We're talking to a user community when you were discussing the applications. Could you tell us a bit of what you can deliver to in terms of fire hazard to this community?
As I said, so here as a user community, of course, we have a representative. So here is TU Delft together with another institute in Italy that are working on new algorithms for fire hazard. And the idea behind is to deliver a risk figure. So by looking at the moisture index that they can calculate, they call it, I think, PMI, perpendicular moisture index. By looking at different parameters, of course, you need some auxiliary data as well that you can upload, and you can tell what is the risk of fire in a certain area. So you can tell, look, based on these parameters, so 70% that a fire will take place in the next days. And that's a very important thing. Of course, we have to see what are the false alarm or the reliability of the algorithm. So I think they tested on past cases, and I think they have 80% of reliability with the algorithm used on images from existing satellites. So we have to see here there are more implications. We have to see what it becomes, but that's the idea behind.
What about the processing power you use on this sensor?
We use a 4-core CPU together with a FPGA and a GPU, so we kind of hybrid computation.
But in total, the execution of software, there's a software or hardware?
It's software. It's software processing.
Software.
Yes.
What in terms of gigaflops?
I don't have now the exact number. I can. Now I don't remember the exact numbers. So I can tell you later.
Is it the order of 10 gigaflops or 1 gigaflop?
I think, I don't know if someone can help me, but yeah, it can be on the order of tens of gigaflops. But I can clarify that.
We are more in the range of half a teraflop.
Hi, Marco. Also, thanks for the nice presentation. I think in your brainstorm sessions, you mentioned that there were applications with 10, 20 meter spatial resolution. And your current design is only 40 to 80. Do you have a design evolution to get to those better spatial characteristics?
In our own roadmap, we have some idea to get to a better spatial resolution. And, but in the end, the outcome was that this kind of 40, 50 meters is really the threshold where, I mean, if you go to lower of that, you start to really get into bigger systems, and because you need more signal. So this was really threshold where you really deliver kind of inspection, early warning, and real-time delivery with a system that's affordable in constellations.
Okay, and the other question I would have is, we talked about stray light earlier, but also things like atmospheric correction can also be very important for these type of measurements. How do you take that into account with, say, a mega constellation of these nano satellites orbiting the Earth?
Yeah. We are applying, let's say, a light correction, let's say. So we have way of taking into account the atmosphere to a certain level. So not actuators running modern on ground, but yeah, that is into the picture.
Any more questions?
So yeah, very nice work. I have a question concerning the temperature dependence of the instrument. Is it temperature dependent? Because the temperature environment in a small satellite could be very challenging.
We did first thermal vacuum test with this EM. Now we are doing we will do actually when the PFM is ready a more extensive ones, and we saw that within the operational temperature we designed for, the system doesn't deform such to really make the performance too low. So there is an influence, yes, but it's on a thermal system, so it's kind of mitigated in that way. And at least in terms of distortion, we don't see it if we do the test with the operational temperature we will find in orbit. At least what we think will be the temperature within the system.
But a number of simulations have been done by cosine during the design phase to understand what is the thermal environment of a CubeSat. So there are some, flight prediction that has been done, and then the test accordingly.
Yeah.
So that we flying blind. Yeah?
And we got actual temperature in flight from previous missions on CubeSat missions with temperature sensors on board. We use that as a...
From ISIS?
No, from others.
Projections were pretty off for this one ISIS mission.
I don't know. From others as well.
But the system is completely one material, so it's prone to be a thermal, obviously within a certain range.
Yeah.
And it's thermally isolated from
Yes.
structure, yes.
Yeah. Indeed. Thanks.
Any other question? Okay, thank you again, Marco.
Thank you.